Hello, I'm Mikhail, and today I'll talk about the results of a collaboration project between the CITIA Research Institute in Brazil and the University of Manchester and the University of Southampton in the UK. We're going to talk about an SMT floating point bit blast API for the verification of C programs. We will start by describing floating points as defined in the IEEE standard, then show how simple programs may contain unforeseen issues. We'll then describe our floating point API and discuss the results of the verification of several C programs from the SVComp 2020. But first, some motivation. Why do we need to verify C programs that use floating points? Floating points are used in many fields, including many mathematical intensive computational areas, such as automated control systems. The main motivation to verify these programs is to prevent bugs. The image you see on the left shows Ariane 5, a rocket that exploded midair in 1996 due to an exception thrown by an invalid floating point conversion. The estimated cost of the incident was $370 million, and its payload, a satellite to study Earth's magnetosphere, was only launched again 4 years later, delaying numerous researches. So, what are floating points? It's one format out of many others that is used to represent real numbers with finite precision. The IEEE 754 standard defines floating point arithmetic used by many processors today. On the left, you can see a die photo of the Intel 8087 floating point coprocessor, the first x87 floating point coprocessor for the 8086 line of microprocessors from 1980. Its purpose was to speed up computations for floating point arithmetic, such as addition, subtraction, multiplication, division, and square root. It also computed transcendental functions such as exponential, logarithmic, and trigonometric calculations. The 8087 was actually the basis for the IEEE 754 standard, released 5 years after the 8087 was released. The 8087 supported both 32-bit and 64-bit long precision format, plus a 80-bit extended precision format that was primarily used to allow the computation of double results more reliably and accurately by minimizing overflow and runoff errors in intermediate calculations. Floating points are divided into three parts: one bit for the sign, an exponent, and a significant part. Both the exponent and significant length depend on the bit length of the type. They represent reals as the formula shown in the slides, and for the scope of this presentation, we assume that base is 2. As an example, the image shows how 0.15625 is represented using a single precision floating point. In C, it will be a 32-bit long variable of the type float. The floating points are divided into five kinds. Both plus and minus infinity are defined in the standard. These floating points represent overflows or the result of non-zero floating point division by zero, as per the Annex F of the C language specification. Both plus and minus zero are defined in the standard as well. Most of the operations will behave identically when presented with either one, except when extracting the sign bit or dividing by zero. Equalities will even evaluate to true when compared positive against negative zeros. The not-a-number special value, or NaN, represent undefined or unrepresentable values, such as the square root of -1 or 0 divided by 0. As a safety measure, most of the operations will return NaN if at least one of the operators is none, to indicate that the computation is valid. Also, NaNs are not comparable. Except for the not equal operator, all other comparisons will evaluate to false. Finally, the floating point is normal if it's a non-zero floating point that can be represented within the range supported by the coding, and it's called denormal or subnormal if it's a non-zero floating point representing various values very close to zero, filling the gap between what can be usually represented by encoding and zero. The standard defines five exceptions for floating point operations. Invalid operation is raised when an operation produces a NaN as a result. Overflow is raised when the result of an operation is too large to be represented by the encoding. Division by zero is raised when we try to divide any number other than zero. By default, these operations return plus and minus infinity. Underflow is raised when the result is too small to be represented by the encoding. And inexact is raised when the encoding cannot represent the result of an operation unless it is rounded. The standard also defines five rounding modes for the floating point operations: round toward positive (RTP), round toward negative (RTN), round toward zero (RTZ), round to nearest ties to even (RNE), round to nearest tie away from zero (RNA). Now let's see how a simple program can contain unforeseen issues. The program on the left is a famous floating point quote issue unquote. Here we compare if 0.3 is equal to the result of adding 0.1 and 0.2. Because of rounding errors, these two values are not equal, as we'll see in the following slides. First of all, none of the values in this program can be accurately represented. X is 0.1 only up to 17 decimal places. Y is 0.2 only up to 16 decimal places. W is not 0.3 but a slightly smaller number. And when we add x and y, the result is actually slightly greater than 0.3, which triggers the assertion violation. The assertion violation arises from the fact that floating points in the IEEE standard are represented as whole numbers multiplied by a power of 2. So only numbers that use prime factors of the base 2 can be correctly expressed as fractions. Since in binary or base 2 the only prime factor is 2, only 1 over 2, 1 over 4, 1 over 8, and so on will be correctly expressed as decimal. So the constants 0.1, 0.2, 0.3 in the program are only approximations. These small programs were our initial target when extending our bounded model checker, called ESBMC, to support floating point arithmetic, since it only supported fixed point arithmetic when it was created. Our first attempt was to use the SMT solvers that offered native support for floating points, Z3 and MATSAT, back in 2017. And the work that we now describe, namely the new floating point API in our SMT backend, is the natural evolution of our research. The support for floating point arithmetic for the remaining SMT solvers in SPMC, Bullactor, EISys, and CVC4. The new floating point API works by converting all floating point types and operations to bit vectors, a process called bitblasting, thus extending the support for floating point arithmetic to any solver that supports bit vector arithmetic. The SMT-FP logic is an addition to the SMT standard first proposed by Rumer and Wall in 2010. The current version of the theory largely follows the IEEE standard 754. It formalizes floating point arithmetic in plus and minus infinity and zeros, nans, relational and arithmetic operations, and 5 rounding modes. There exist some functionalities from the IEEE standard that are not yet supported by the FP logic, as described by Martin Brain in a 2015 paper. However, when encoding C programs using the FP logic, most of the process is a one-to-one conversion, as we described in a 2017 paper. In practice, encoding programs using the SMT floating point theory has several advantages over the fixed point encoding. The main one is the correct modeling of C or C++ programs that use the IEEE floating point arithmetic. Our bounded model checker, ESBMC, ships with models for most of the C11 standard functions. Floating point exception handling, however, is not yet supported. The encode algorithms, however, can be very complex, and it's not uncommon to see SMT solvers struggling to support every corner case. Currently, various SMT solvers support the SMT floating point theory, like Z3, MATSAT, CVC4, Colibri, Solonar, and Upset. ESBMC implements the floating point encoding for Z3, CVC4, and MATSAT using their native ABI. Regarding the support from the solvers, Z3 and CVC4 implement all operators, while MATSAT implements all but two, the FP RAM remind operator, and FP-FMA, the fused multiply-add operator. The three solvers offer two non-standard functions to reinterpret floating points to and from bit vectors. These functions can be used to circumvent any lack of operators and only require the user to write the missing ones. Note that this is different from converting floating points to bit vectors and vice versa. Converting to bit vectors follows the rounding mode defined by the IEEE standard, while reinterpreting the floating point as bit vectors returns the bit vector format of the floating point. We use these functions in our backend to implement the fuse multiply add operator for Z3. The implementation of our floating point API is based on the code of the IEEE 754 standard. However, before we can discuss the algorithms in our floating point API, we first need to describe the basic operations performed by most of them. The usual four-stage pipeline: unpack, operate, round, and pack. In the unpack stage, the floating point is split into three bit vectors: one for the sign, one for the exponent, and one for the significand. In our floating point API, the unpack operation also adds the hidden bit to the significand and unbiases the exponent. In the operate stage, the conversion and arithmetic operations are performed in the three bit vectors. Depending on the operation, the bit vectors need to be extended. For instance, during the fused multiply add operation, significand has double its original size plus 3 bits, and the exponent has 2 extra bits. Since in the previous stage the operation was performed using extended bit vectors, in the round stage, the bit vectors are rounded back to the nearest representable floating point of the target format. Here, guard and stick bits in the significand are used to determine how far the bit vector is from the nearest representable, and the round mode is used to determine in which direction the floating point will be rounded. The exponent bit vector is also checked for under or overflow when rounding to create the correct floating point. For instance, infinite might be created if the exponent is too large for the target format, or minus or plus 0 might be created if the target format cannot hold a very small subnormal. Finally, in the pack stage, the three bit vectors are concatenated to form the final floating point. Internally, we grouped the operations into seven groups: sort constructors, rounding mode constructors, values constructors, classification operators, comparison operators, conversion operators, and arithmetic operators. The sorts follow the definition shown in the table for the bit vector sizes. We do not support the 80-bit long double extended precision format used in some processes. Instead, we use the 128 bits for quadruple precision. The floating point API supports all rounding modes, even though the C standard does not support RNA. These are encoded as 3-bit long bit vectors. Floating point literals plus and minus infinity, plus and minus 0, and nans can be created in our floating point API. All algorithms in our floating point API assume one hidden bit in the significand. For nans, we always use the same bit pattern: exponent all 1 and significand it's 0000 and this last bit 1. This is the main difference from our floating point API to the SMT standard. In the SMT standard, you cannot have negative nams. The classification operators consist of algorithms to classify normals, subnormals, zeros and infinities, regardless of the sign, nams, and negative and positive floating points. The operators work by unpacking the floating point and comparing the bit vector against the definitions. The supported comparison operators are greater than or equal to, greater than, less than or equal to, less than, and equality. The first three are written in the terms of the last two. All of them evaluate to false if one of the arguments is none. This check is done using the non-classificator operation. The floating point API can convert floating points to signed or unsigned bit vectors. This operation converts the floating points to bit vectors, always rounded towards 0. This operation generates a free variable if it cannot represent the floating point using the target bit vector. For instance, if the floating point is out of range, it is plus or minus nam or plus or minus infinity. minus zeros is always converted to positive zero. Floating points to another floating point. Convert the floating point to a different format using a round mode. Plus and minus num, plus and minus infinity, and plus and minus zero are always convertible between floating points. But convert between format migrate minus plus infinity if the target format cannot represent the original floating point. This is another point that we are different from the SMTFP logic because in here we preserve the sign for num when converting between formats. Finally, signed or unsigned bit vectors to floating points. This convert bit vectors to the nearest representable floating point using a round mode. It might create plus minus infinity if the target format cannot represent the original bit vector. Lastly, our floating point API supports the following arithmetic operators. Absolute value, which sets the sign bit for the floating point to 0, and negation, which flips the sign bit of the floating point. These two are also formalized differently in the SMTFP logic. While we apply the described operations to name also, in the SMTFP logic, these operations simply return the name without changing them. In the addition operator, the significants are extended by 3 bits to perform the addition. The exponent is extended by 2 bits to check for overflows. The algorithm first aligns the significants and it adds them. In the subtraction operator, the algorithm negates the right-hand side of the expression and uses the addition operator to perform the subtraction. In the multiplication operation, the length of the significant vectors are doubled before multiplying them, and the exponents are added together. The final sign bit is the result of a short operation using the sign of both operands of the multiplication. The division, the length of both significand and exponents are extended by 2 bits. After that, the bivector subtraction are used to calculate the target significand and exponent. The fuse and multiply add, the significant length is doubled plus 3 bits to accommodate both the multiplication and the addition. And the exponent is extended by 2 bits. The first two operands are multiplied and the result is aligned with the third operand before adding them. This is the multiplication followed by an addition without rounding between the two operations. In the square root operator, neither the significand or the exponent is extended since the result always fits the original format and can never underflow or overflow as per the operator definition. Finally, all arithmetic operations in the floating point API that take more than one floating point as an argument assume that the floating points have the same format. This assumption is not a problem when verifying C programs because of the type promotion rules in the language that already ensure this precondition. Now we are going to present the experimental evaluation we performed in this research. We started by comparing the several SMT solvers, 8 to be more precise, and we're going to compare them while verifying 466 benchmarks from the subcategory Reach Safety Floats from SFVCOM 2020. These are all C programs. Here in the list of SMT solvers, FP2BVIR is our BitBlast API. So on top of using Bolecta, Yices, Z3, Matsat, and CVC4 with our API, we are also comparing Z3 and Matsat with their native API. Bolecta, using Lingually and our FP2BV API, reports the highest number of correct results, 421, followed by Matsat using their native floating point API, 414. Matsat, using our floating point to BV API, presented the fewest number of correct results, 329. The results show that the Z3 with its native floating point API and Z3 with our FP2PV API produce very similar results, 390 and 387 respectively. This result is expected since our FP2BV API is based on the bit blasting performed by Z3 when solving floating points. The number of variables and calls generated in the CNF format when using Z3 with its native floating point API is around 1 to 2% smaller than the number generated when using our FP2PV API. The smaller number explains the slightly better results. We assume this is a result of optimizations when Z3 performs the BVLAS internally. MudSat results show that the API can solve 85 more benchmarks than MedSat with our API within the time and memory limits. These benchmarks contain chains of multiplication. They thus require high computational effort during the proportional satisfiability search. Given that we replace all high-level operators by bit-level circuit equivalents, the blasting process, we end up destroying structured word-level information in the problem formulation. Therefore, this result leads us to believe the MATSAT ACDL algorithm is somehow optimized for FP operations. Unfortunately, MATSAT is free but closed source, so we cannot confirm this. The total verification time for each solver is illustrated in Figure 2. And again, Blue Lecter Linkerlink using FP API was the fastest solver, thereby solving all the problems in 46,100 seconds. It is followed by Bullactor Carical with our FP2PV API and the ISIS using our FP2PV API. Overall, Bullactor Lingerling with our FP2PV API presented the best results. It correctly verified more programs while also being the fastest solver. This is the first result of our research. YesBMC, when verifying these programs, produced no incorrect results. Although we cannot formally prove the algorithm is sound and complete, empirical evidence suggests it. Finally, we're going to compare our best approach, the Bolacta with FPBV, against all the verifiers. ToLS, CBMC, CPA-SAC, Divine, Pascal, Pinaka, Symbiotic, and Variabs. All these solvers were part of the SFEComp 2020 website, and we got the binaries and scripts to run the tools from the competition website. These are the tools results. Overall, Variabs was the best one, solving 435 benchmarks, followed by Pinaka and YesBMC, using Bolactor with Linkerlink and our FP2PV API. Both Variabs and Pinaka use k-induction and they generate new programs that are verified by CBMC, while ESBMC is using an incremental approach here. We believe that if Variabs or Pinaka use ESBMC, they will probably have better results since ESBMC with Bolactor and our API was the third best verifier in the comparison. This brings us to our second conclusion. Our floating point API is on par with all the state-of-the-art tools. Variabs and Pinaka implement several heuristics to simplify and check for satisfiability using CPMC, while YesBMC using an incremental approach produced close results. YesBMC was also slightly faster and provided a few more results than CPMC, which lead us to believe there are two will great benefit Variabs and Pinaka if used as backend. And we're gonna finish our presentation here, but before we end it, just a quick look into the future of our floating point API. So we decided to decouple it from YesBMC, given the great results they had, and we are developing a C++11 library called libkamada. You can find it in the link in the slides. Version 1.0 will probably be released late summer and will include the FP API as a separate library on top of every other solver, so anyone can benefit from it. And it will also be integrated into LLVM in CLI once the code is stable enough. And that's it. Thank you very much for listening. And this is my email. If you have any questions, feel free to contact me.